3.9 Related rates. Essential question: can I calculate a rate that may be difficult to measure from a rate I know? Air is being pumped into a spherical balloon so that the volume increases at a rate of 100 centimeters cubed per second. How fast is the radius of the balloon increasing when the diameter is 50 centimeters? All right, so what we would like to do is, the strategy is to get the given information into math notation. And our first given information is right here. So we're going to say dV dt is equal to 100 centimeters cubed per second. And this makes sense because centimeters cubed is a volume and seconds does represent time. I'm being asked to find how fast the radius of the balloon is changing, so I put that in math notation, dr dt, at the moment when diameter is 50, or I can say radius is 25. So I've done this portion and this portion. We want to use a formula that relates the information. So we want to use a formula that uses V and it uses R. And that will be the volume formula for a sphere. I want to take the derivative with respect to time on both sides. This is going to require implicit differentiation. So this will be dV dt. And then this is a constant, so I'll just write 4/3 pi. And now I'm going to treat R as a differentiable function. 3r squared times dr dt. Okay, understand that we have a number for this and we have a radius. So if we substitute into this formula, we should be able to get what we want to know, which is dr dt. So this is going to be 100 equals, I can reduce by here, 4 pi, and then this is going to be 25 squared dr dt. Now dr dt will be equal to 100 divided by 4 times pi times 25 times 25. And we know that 100, and this is going to be 100. So my answer is going to be 1 over 25 pi, and our units is going to be centimeters per second. So related rates is what this unit is called, and it's called related rates because we have an equation that has two different rates and it's showing us how they relate to each other. In GeoGebra, they have an example of not a sphere growing, but of a oil slick that's getting bigger. So as it gets bigger, notice the area is changing, and if you think about the rate at which the area is changing, that would be a derivative, and you can see the derivative is different at different times. Okay, let's look at another problem, very typical, the ladder problem. We have a ladder that's leaning against the wall. We've done this in geometry, but it was a static problem. Nothing was moving. In calculus, we're going to have this ladder sliding. This point is moving, it's sliding out, and the top of the ladder is sliding down. We want to write the given information in terms of calculus. So we see that the bottom of the ladder is sliding at 1 foot per second. So I'm going to say, since this is the bottom, dx dt is equal to 1 foot per second. And we want to find how fast the top of the ladder is sliding. We want to find dy dt at the moment that the tip of the ladder is 6 feet from the wall. So this gives us our information, and we write down what we know. Now we're looking for a formula. And the formula that we're going to use that involves x and y is the Pythagorean theorem. So we're going to take the derivative with respect to time on both sides. This is going to require implicit differentiation. You're going to treat x and y as differentiable functions. 2x dx dt plus 2y dy dt is equal to 0. We can divide both sides by 2. And now we're going to have values for x. X is 6, dx dt is 1. Now when x is 6, at the moment that x is 6, y has to be 8 because this is a 3, 4, 5 triangle. Or you can just use the Pythagorean theorem if you've forgotten. 8, and then this is dy dt is equal to 0. So dy dt will be equal to negative 3/4, and we're going to label it feet per second. Now this makes sense that this is a negative number because this distance is getting smaller and smaller, so it's decreasing, and that negative does indicate decreasing. Okay, the ladder problem in GeoGebra. This kind of gives you an idea. See the ladder, the ladder is not changing, but the distances from the wall and on the ground are changing. All right, let's take a look at another problem involving volume once again. A water tank in the shape of an inverted cone with a base of 2 and a height of 4. If water is being pumped at a rate of 2 cubic meters per minute. Now that's a dead giveaway for volume with respect to time. dV dt is equal to meters cubed per minute. We want to find the rate at which the water level is rising. Define dH dt at the moment when it is 3 feet deep. Okay, and our formula we're going to be using is our volume formula. Unfortunately, the formula has 3 variables, V, R, and H. And I don't want to take the derivative until I can only do it in terms of V and H. So I'm going to go to the figure and I'm going to see if there's a relationship between R and H. And sure enough there is. These are similar triangles. And with similar triangles, the sides are in proportion. So I know that R is to 2 as H is to 4. That means the radius is the height divided by 2. And that's what I'm going to substitute into here. So instead of R, instead of R squared, I'm going to write H squared over 4 times H. Clean this up a little bit, 1/12 pi H cubed. Now I have my formula in terms of V and H, and now I'm going to take the derivative with respect to time. So implicit differentiation, dV dt equals 1/4 pi H squared times dH dt. I just took this over and did a little reducing here. Now I do know this number and I do know H, and I'm going to stop right here because I think you can do the rest and get dH dt on your own. Okay, here's GeoGebra relating the conical tank problem again. And this is relating the height with respect to time. And you could see at different times the rate at which the water level is changing differs. It's not a constant relationship. Here's the strategy for doing related rates. Let's look at another problem. This is a typical problem where two cars are heading in directions. Either they can go toward each other or away from each other. In this situation, car A is traveling west and car B is traveling north. Now I'm going to write this in terms of calculus. So I'm going to say dx dt is equal to negative 50. Why did I say negative? Because this distance is getting smaller and smaller. That's decreasing. dy dt is this, the northbound, and again I put a negative because it's decreasing as well. They're telling me to find this rate of change, dz dt, when x is equal to 0.3, y is equal to 0.4. The formula I want to use is the Pythagorean theorem. Very similar to the ladder problem, except the ladder had a constant hypotenuse where this is not. Now I'm going to take the derivative with respect to time, so I'm going to get 2x dx dt plus 2y dy dt. This is using implicit differentiation and using the chain rule, dz dt. Now all of these 2's are going to be, I can multiply them out. I'm going to have a value for each one of these. The only one I don't have a value for is z. So let's see what's happening here. If at the moment that x is 0.3 and 0.4, this is going to be 0.5. So I will have a value for every one of these except dz dt, which I can solve for. And I'm going to let you do that. Okay, GeoGebra has an interesting little demonstration with trains. Now they're not the same situation as the cars, but again you can see the distances relating to each other. Okay, this is our last problem. A man walks along a straight path at a speed of 4 feet per second, and I'm going to change this to calculus. So this distance right here, dx dt, is 4 feet per second. We are looking for what the rate at which the searchlight is rotating. So we're looking for d theta dt at the moment when the man is 15 feet from this closest path. So I've changed everything into math notation. I found out what is unknown, and now I need to look for a formula that relates x and theta. And that's going to be our tangent function. Tangent theta is equal to x over 20. All right, now I'm going to take the derivative, and this is going to give me secant squared theta, use a chain rule, d theta dt, is equal to, and I think I should have had an x here, so that's going to be equal to 1/20th dx dt. All right, so I'd like to find d theta dt, which is this value right here. So I'm going to write d theta dt is equal to, now secant squared theta is the same thing as 1 over cosine squared theta. So when I put it to the other side, I'm going to get cosine squared theta all over 20 and times dx dt. I do have dx dt, and now I'm going to help you figure out what cosine theta is. Okay, cosine theta, remember, is adjacent over hypotenuse. And at the moment I'm looking at it, x is ending up being 15. So this is going to be another 3, 4, and this will be 5. So cosine of theta will be 20 over 25, or 4/5. So when you want to substitute for cosine theta, you're going to put 4/5 in there. You're going to square it, divide it by 20, and then put in the value for dx dt to solve the problem. And this is the end of the screencast.